Alright, so we will attempt to have a few basic lessons in so-called ENT or elementary number theory, and we'll keep it really simple in the beginning, but at the same time we'll make sure that we'll cover extremely crucial ideas. What we're going to do today goes by the name of the fundamental theorem of arithmetic. Well, it sounds very fancy, but it's a very simple fact that we are well used to, and what I want to show is that it plays a role in problem solving. Now, to exemplify this, I shall completely take help of this book. So I do hope that most of you have a copy of this book, and well, if you don't have it, you must definitely buy this. This is a worthwhile buy. Now, it has got two main chapters on number theory, and because it's a difficult topic to navigate very carefully, I shall take help of this book and follow this book very diligently. So I shall keep referring to the book for problems to illustrate, and this chapter is chapter 3, Divisibility and Remainders. Now, what exactly is the fundamental theorem of arithmetic? So if you take some number, then you can always break it down into a product of primes, and if you can't, then that number is called a prime number. So any number n can be written as a product of prime numbers, and these prime numbers will be sometimes you can have the prime number occurring repeatedly. So the prime number can be raised to some power, and this to some power, and so on. And this then is the general representation of the number, which is broken down into the product of primes, and this is called the prime factorization. So what does the fundamental theorem of arithmetic say? It says that this prime factorization is unique. Now, we shall not worry too much about the proof, but we'll go ahead and see how the simple, nice fact plays a role in elementary number theory. So, just to give you an example to get used to it, suppose the number is 72, then this you know is 8 into 9, but 8 can be written as 2 cube and 9 can be written as 3 square, and therefore one can think of the usually it is usual practice to put the numbers in increasing primes. So here you can see that P1 could be 2 and K1 could be 3, P2 could be 3, K2 could be 2, and so on. Now, this is the prime factorization of 72. So, what this immediately gives us a rather crude test of divisibility. It's very inefficient, but nevertheless, I don't think that we should neglect using this idea when we think about problems in number theory. So, suppose somebody says, is 72, is it divisible by 24? And this is the notation for is 72 divisible by 24? And in this case, we know it is yes. But the way to think about it in terms of prime factorization is, what are the prime factorization of 24? So it's 8 into 3, so 2 cube into 3. And this one we already know is 2 cube into 3 square. Now, you can see here that all the primes in 24 should appear in 72, and they do appear, and therefore 24 divides 72. So like I said, it is giving us a very crude test to test divisibility. Now, suppose the question says, is 74 divisible by 24? So the question is does 24 divide 74? And we know the answer is no, so this is the way to say that 74 is not divisible by 24, or 24 does not divide 74. But if you want to think in terms of the prime factorization test, then this one we just saw is 2 cube into 3, and this one is 37 into 2. Now here you can see that 2 cube does not occur here, and neither does 3, and for both these reasons we can say that 74 is not divisible by 24. So let me give you one more simple number theory fact that we use, which is based on thinking like this. So here is a fact that we should use quite often. So I'm just going to state it. So for example, if somebody says that a number d divides AB, okay, so AB, the product of two numbers, is divisible by d. Further, if we know that the greatest common divisor of D and A is 1, and what this means is that there is no common factors between D and A. And another way to normally say this is that A and D are co-prime. Now if this happens, and we can conclude from here that this implies D divides B. And how are we going to reason this out? Since there are the prime factorization of D does not, the prime factors of D do not occur in A because of GCD being 1, which means that all the prime factors of D are actually in B. So all the prime factors of D appear in B because D divides AB, and that means that if all the prime factors of D appear in B, then we can definitely say that D divides B. So here's a very beautiful result, and we can argue in terms of the prime factorization theorem. So what I'm really trying to tell you is that it's a very simple basic fact, but it's going to play a big role in the way we think about the basic ideas of number theory. Now, what we're talking about is really, we already started getting into this very nice idea in a long drawn out battle of divisibility. So now what I should do is, this is right in the beginning of the book. I'm talking about the 4th or 5th page of this chapter on number theory in this wonderful book. So I'm going to pick up one or two problems right from here so that you can go back and also refer to the same problem. But I shall stick to the theme of trying to tell you that this is really a fundamental thing that keeps occurring in the way we think about problems in number theory. So let me take up an example from the book. So here's a nice problem from the book. This is problem number 11 on page number 23 of the book. So please do look into this page. Now the problem goes like this. If A and B are such that 56A is equal to 65B, this implies A plus B is composite. So we have to argue that given this 56A is equal to 65B, we have to argue that A plus B cannot be prime, but it is composite. So let us go very simple. Let us break this up into prime factors. So now you can see here that this one is 8 into 7, so 2 cubed into 7. A is equal to 13 into 5 times B. So we have broken up the number 56 into primes, and we have broken up the number 65 into primes. Note that the statement says that the number on this side and the number on this side is same, which means that the prime factorization of the LHS will be equal to the prime factorization of the RHS. That is indeed the statement of the prime factorization theorem. Now if you look at the LHS, these two primes have to occur also here, which means that these two primes are actually in B. Similarly, these two primes have to occur in A. Now what this means is that A definitely has got a 13 in it and a 5 in it, some factor which may not be so much interested in. Similarly, B, we just call it K, B is definitely going to have 8 into 7, 56 in it into some number K. So ultimately what we are saying is, we can break this down equation as 2 cube into 7 into 13 into 5 into K is equal to 13 into 5 into 2 cube into 7 into K. Now this makes a lot of sense, but what we really have concluded here is that A is such a number and B is such a number. Now from here we proceed to find out what is A plus B. So A plus B now is equal to 65K plus 56K, and this happens to be 121K, and this then is definitely not a prime because it has got 11 square as a factor. So A plus B is got 11 as a prime factor, which occurs twice for sure, and therefore we conclude that A plus B is composite. So as you can see, this is a very nice problem from the book, and all we have done here is use the fundamental theorem of arithmetic or the prime factorization of the number to argue out the end answer. Let me just pick up one more problem from the same page for this lesson. It says that what's the smallest n such that n factorial is divisible by 990. 990 should divide n factorial. Now once again, I just want to highlight the first step. The first step is to think of the prime factors of 990. Now this is 9 into 11 into 2 into 5. So this theory is the, this is, okay, I can write 9 is 3 square. So these are the prime factors that have to occur on the right hand side in n factorial if 990 is to divide n factorial. So we have to think of n factorial such that all of these numbers appear in n factorial. Now if you look at it, 11 is a prime, and there is no way that you're going to have 11 in n factorial unless you go at least up to 11. And what you can see here is that there's no way that you can avoid going up to 11, because that's the only way that 11 appears on the right hand side at least once. Now what about the rest? 3 square. Well, there is a 3 here and there is also 3 here, so there's nothing to worry about 3 square. And what about 2? Yes, no problem, in 2 occurs so many times. What about 5? Yes, 5 occurs. So everybody on the left hand side do occur on this side, and of course 11 does occur here, and you have to go up to 11 factorial, and the answer for this problem is that the smallest n is 11, and for sure 11 factorial is divisible by 990. So with the help of these 2 or 3 problems, I hope I have just tried to illustrate how the simple theorem comes into play. Maybe we just do one more simple problem before we wind up. It's there in the book. It says that, although we can quickly mention 2 problems. So here's a first simple example of a Diophantine equation, and he says that find x and y, and when we say find x and y in number theory, we typically mean integers, or we could mean natural numbers, and it will be explicitly mentioned. Now this problem says x square minus y square is equal to 31. Now what is the role of the prime factorization theorem? Now 31 being a prime, it can only be written as 1 into 31 or 31 into 1. And usually this is the simplest idea for solving a Diophantine equation. Now the LHS can be factorized into x, and what this means is that that x minus y is a number, x plus y is a number, and these two numbers are to be the numbers on the right hand side, which can only be factorized either as 1 into 31 or 31 into 1. So the only way that one can think of solutions for this problem is x minus y is equal to 1, x plus y is equal to 31, or x minus y is equal to 31 and x plus y is equal to 1, and you might get two answers in integers. So why are we discussing this problem in this particular video? It's because we have used the prime factorization of 31 to reason out a solution to this Diophantine equation. So there are quite a few problems here, but I shall just do one more before I wind up. And this one, by the way, this is problem number 12. This is problem number 12 in the book on page number 23. Okay. So now let's look at one last problem before we wind up this lesson, and I hope, like I said, to take the help of this book to navigate through the most simplest but wonderful ideas to get us started with serious elementary number theory, E and T. So let's not forget that we're doing E and T. Now what I want you to let's do this one last problem before we wind this up. This one says that suppose that number n has a prime factor pq, then how many divisors does n have? So p is a prime, q is a prime, n is pq, and how many divisors does n have? Well, definitely n has got 1 as a divisor. Now you can see that if d is a divisor of n, the prime factorization of d, the primes occurring in d have to occur in n. So for that one can try p, because d can be p, or d can also be q, or d can be pq, and in all these cases, as you can see, the prime factorization, the prime factors in d occur in n, and therefore d divides n. So in this case, you can see that the answer is 1, 2, 3, 4. So the number n has 4 divisors. Okay, the slight extension to this problem is what happens if n is p square q. So how do we argue now? You can have n, 1 of course is a divisor of p squared q, but how about also other possibilities for d being a divisor of n? So we should look for combinations of these primes here. So you can have p, or you can have p squared, or you can have q, or you can have pq, or you can have p squared q, and of course you can have okay, this is it. So these are the possibilities for the prime factorization of d such that d is a divisor of n. And how many numbers do we have here? 1, 2, 3, 4, 5, 6. So this time n has got 6 divisors. So the problem further continues and asks for generalization of p raised to n and q raised to m. Now I think we shall leave it to you to think in the same way and find out the number of divisors of n. But like I said, my main purpose here is to use the fundamental theorem of arithmetic and to use the prime factorization as a way to deal with these questions. So with that, we'll come to the end of this first lesson, and there are a few more simple lessons which you can pick up very fast from this book, and that will definitely get us onto a firm ground and tackle problems from elementary number theory, tougher and tougher problems very soon, that's for sure. See you then. Bye. All the best.